Now let's introduce some simple concept of group. For example, in some cases, the number of elements in set is limited. Like we have mentioned, the corresponding G, its elements are from 0 until n-1. There are a total of n elements. Then this kind of group is known as a limited group. But under certain circumstances, the number in G is unlimited. For example, corresponding to the Euclidean space, after the rotation, the number of rotation angles is unlimited. We know as an unlimited group. For a limited group, we define the number of elements of a limited group G as the order of the group. Then we will realize since it is a group, it may potentially contain subset, so corresponding to a big group G. If several units were taken out from the group, under its original operations still form a group, we know it as subgroup. These are some common and obvious concepts. But there is a question that we need to think back. We have just mentioned the group may need to satisfy the law of association. Then, from what we have learned from the addition, other than law of association, is there anything else? Can all of you recall that there is something known as a commutative law, which means A plus B and B plus A are the same. But in a group, we do not request that all the elements with certain operations may satisfy this law. Only in some cases, they will satisfy commutative law, and those groups which satisfy this law can called as a commutative group. Because 2A and B, they are binary operations, A calculates B is equal to B calculates A. This group is also known as an abelian group. Other than this characteristic, we want to perform in-depth analysis. For example, how many identity elements are there? Then think, there is only one 0 in addition operation. It is the only identity element. Under multiplication, there is only one as the identity element. Therefore, we can place a guess. In a group, the identity element is unique. We definitely will realize that if there are two identity elements, then the two identity elements will carry out their calculation operation. They will still finally become a single identity element. Then naturally, they are the same. At the same time, cancellation law does exist. For example, A calculates B is equal to A calculates C, and then if we calculate the inverse of A for both sides, it simply means B is equal to C. Therefore, cancellation law holds. Well, at the same time, because the corresponding identity element is unique, then the corresponding inverse of each element is also unique. And through the calculation inverse element, we will manage to get, for example, A, B, C until C. They contains many elements. Their inversion should be equivalent to switching their order to the inverse of C continue until the inverse of B inverse of A. Why it is so? We will realize, in fact, we use C inverse, B inverse, A inverse times A, B, C. Multiplying the pairs step by step will finally obtain identity element E. Therefore, these two elements practically form the inversion relationship, and at the same time, while we are studying on the limited group, we will realize in a limited group, any of the elements after numerous calculation between it and itself, it will finally get an identity element, which means for some G, there is one element A, then we should be able to find the smallest positive integer R, make A to the power of R, which means A is calculated with itself for R times, and its result is just the identity element. Besides, what does the inverse of A equal to? The inverse of A is equal to A to the power of R minus 1. Why? Actually, we can think through in this way. Because there are totally G elements in G, which means the order is G. Then we can set A squared until A to the power of G plus 1. According to pigeonhole principle, we will know in this G plus 1 number of elements, there will be two identical elements. If there are two which are identical, suppose two elements A to the power of L and A to the power of M are the same, then we can assume that M is less than L. They are between 1 and G plus 1. At the same time, we can use the cancellation law, then we will realize E should be equal to A to the power of L minus M. Let R equal to L minus M. Therefore, this element A, after going through several self operations, will manage to get the identity element. And according to this kind of situation, naturally we will also get the inverse of A equal to A to the power of R minus 1. Well, for the same time, we can still take an A element A squared until A to the power of R. Out of then, it will form a subgroup under the original operation.